Okay, you're very welcome. Can you hear, can you see it fine?
Yes.
Okay, great. Okay. So this is based on my master thesis in industrial engineering, actually. So you can also see that I get a master's degree in physiology at McGill. But that happened after building this model, and I was able actually to successfully take and pass courses in advanced renal physiology and advanced endocrine physiology after, because of having built that model by then. So it's a closed loop system dynamics model for body water disorders, and particularly for hyponatremia or antidiuretic hormone induced hyponatremia. It's a popular name, water intoxication. It's primarily acquired by patients during hospital stay, so it's an important fluid disorder. So our motivation was, of course, for me, the motivation as a master student was to have a master thesis. But other than that, the idea was to find a dynamic problem, a dynamic and interesting medical problem. And I came up with multiple medical problems. And most and more obvious ones that were modeled by kind of previous students recently, thyroid disorders, right, pituitary, hypothalamus, etc. Those endocrine-related disorders. Those are the most obvious ones. Another one that I was more interested in was the body fluid electrolyte disorders. So in order to do so, and then convert it to a kind of a game interface, etc. But then we realized that, of course, you first have to model the normal physiology, right, for body water regulation, and then you have to use the same model to come up with the disease physiology, and then turn it into an interactive game, etc. Which each of these steps take a lot of time. But I was able to come up to this point. Like I'm going to introduce the interactive game, and then now one of my PhD students, she's going to take over this research. She's actually working on this research, conducted some literature surveys, etc. Let me see. Oh, the study was also by then the winner of the Dana Meadows Award for the best student paper. And by then, 2006 was a long time ago. The Lupina Prize wasn't there, unfortunately. So I don't know, but it could have get that one too. So some background about and problem description and background. So regulation of body water and its appropriate distribution throughout the body it's important in almost every field of medicine. So it also has been thoroughly investigated the last century. So in health, the total body water and its distribution is maintained between very narrow limits, but by two distinct yet interactive systems. They respectively regulate the body water itself and the sodium content, right? So these are the task is accomplished by two different and interactive control systems, which within themselves are coupled feedback loops. I mean, both of these systems, one of them focuses on the body water content and the other one on the sodium content. So and it's important to make this distinction because any hormonal or any other influence which alters the balance of one of these systems inevitably affects the balance of the other one, right? And all hormones regulating this electrolyte and water balance, they exert influences on the circulating blood volume also, and eventually on the systemic blood pressure, like in some degree, more or less. So it's important to differentiate those clinical abnormalities for sodium content, which relate to cardiovascular, blood pressure, etc. related disorders from those of the body water regulation, which are dysnatremias, hyponatremia, hypernatremia, etc. So in this study, we are interested in dysnatremias, so disorders of body water homeostasis and not metabolism, because water is not metabolized. So I was reminded by this by a physiology professor very correctly. So then I changed it to homeostasis. So the thesis, I think the name in the thesis was metabolism, then I changed. So loss of water leads to hypernatremia, right? Which is bad because it means widespread functional disturbances in the brain. On the other hand, in hyponatremia, which is the disorder that I'm going to show you, but you can use basically the same model for both for hyponatremia and hypernatremia, basically. So it means accumulation of total body water, which means cell swelling, disturbances in central nervous system, and particularly if you want to treat it, like, so you have to treat it, but the problem is if you treat it too fast, that also itself poses some challenges. So they are both of these disorders are associated with changes in the cell volume. So they are very common in hospitalized patients, not just sodium, like hypokalemia, potassium, calcium, etc. Let's assume a patient comes to the hospital for some other problem, and while she's getting treated, she also acquires hyponatremia. So that's why, like, hyponatremia is important. It's the most common and serious disorder encountered in hospital settings. So most cases of it, they're mild, but diagnosis and subsequent management is still delicate. So it can be a challenging problem, in part due to this complex nature of the body fluid system. And if it is severe, it's associated with a definite, like, substantial mortality and morbidity. As I said, you can die out of drinking water, like, fast and too much and too fast, which is interesting. So the main risk is brain cell swelling. So as I said, it requires prompt treatment, but also there's a delicate balance between the treatment itself, because you should weigh the risk of hyponatremia against the risks of correction. So any problems up to here? I mean, any questions up to here? So this was sort of the background of what's going on. So
actually,
some
yeah,
basic
quick question.
Yeah, Ed, go ahead.
If you go back, you mentioned that rapid treatment can lead to death. Is that
Yes.
due to delay?
Yes.
Is that due to delays in distribution of sodium when you administer it? If it goes into this the blood compartment, does it not get distributed to the total body water? I mean,
Yeah, that's true. And so there are multiple different ways for the treatment of hyponatremia. And that problem particularly happens during intravenous saline infusion. So as you said, if it's too fast, the body cannot adjust. So that's why I think doctors have some heuristics about the correction of hyponatremia, hypernatremia-related electrolyte disorders. So they try not to exceed, let's say, 5 milliequivalents per liter per minute, something like that. So they have some instructions about that, but it's really based on heuristics and not like really on following any other more rigorous procedure. So
I'll be patient for the rest of your talk. I'm sure we'll hear more about it.
No, feel free to interrupt. So this is supposed to be a casual conversation, I think. I thought so, I don't know. So the major division of body water, you can think of it as like relative to the cell. So there are two compartments, extracellular compartment and the intracellular compartment, right? The major division is into these compartments. The cells are separated from their environment by the cell membrane. So the most abundant substance of this extracellular environment is sodium, and the most abundant substance for the intracellular environment is potassium, and these are mostly restricted in their respective compartments, and particularly potassium. It doesn't move very easily. So under usual conditions, control of extracellular osmolality means almost the same thing as controlling your extracellular sodium concentration, which also means, since blood is part of this extracellular compartment, your blood sodium. So let's call it blood sodium maybe from now on. Blood sodium means the number of particles osmoles per liter of water, amount of sodium contained in 1 liter of extracellular fluid. So they have to share the same osmolality. There's some math, so you multiply it by 2 and add a constant, but pretty much that's the equation. So, and this one is the main feedback system for body water regulation. So the first out of these two systems. So it's the antidiuretic hormone thirst system. It responds to, let me show you what it responds to. Okay, so it responds to variation in extracellular or blood sodium concentration, right? And the body can do it by changing both the input and the output. Your blood sodium concentration goes up, it stimulates drinking. At the same time, you can also, the body also causes an increase in antidiuretic hormone, which can change the concentration of the urine, right? In turn, it decreases the urine. So the body can basically change both input and output at the same time. And this system works very fast, which you can also understand by looking at the half-life of this hormone, which is around 6 minutes, 8 minutes. So it's kind of, there's a daily variation. So that mechanism is often referred to as the thirst antidiuretic hormone mechanism by itself, because you need both of these components to for it to work properly. So it regulates the water intake by controlling the perception of thirst, water output by antidiuretic hormone, which is responsible for urinary concentration and dilution. And it looks at the extracellular osmolality, or as I said, the blood sodium concentration. And there is a set point for blood sodium concentration, so it's kept under a strict limit, which is determined by the hypothalamus itself. So in this model, we assumed it to be exogenous to our problem. There might be another set point for it. But let me ask you this question. I try to make it interactive. So what do you think is, so what is the point of having a constant blood sodium concentration? What is the biological meaning? Because just keeping the blood sodium concentration constant at a certain number by itself doesn't mean anything. There needs to be a biological advantage. And I gave you some hints, what is previously in the previous slide. Do you have any idea about what is the advantage of keeping your blood sodium concentration constant in terms of the water balance?
Potassium.
Who says that?
I said that, Wayne. Potassium is really important for signaling and whatnot.
Elaborate. What is it?
Oh, you told us it was a hint. The hint was potassium in the previous slide. And I know that potassium K is really important. Ed probably knows a lot more about this than I do.
Yeah, but I also said potassium doesn't move. So it's wrong, but it was a good it was a good try.
Okay, I almost said that, but I didn't jump in quick enough. But the cell volumes are very sensitive to
these concentration
osmolarity. Yes. So you should know that, Wayne, from the brain swelling.
Yeah, that was the hint. Yes, the brain swelling was the hint from the previous slide. So if you look at this one, concentration and content, like by controlling the concentration of blood sodium and the intracellular potassium doesn't change much, right? Potassium is there. Basically, it means controlling the cell volume. And why is it important to keep the cell volume constant? It's important for maintaining optimum function for most cells, but also, if you think about it, particularly important for our brain, because like cells are confined in your skull, so they don't have much place to escape if there is brain cell swelling. So unfortunately, there will be some irreversible consequences. So that, I think, is the biological meaning rather than keeping a constant set point and number constant or something like that. So the second system is also composed of multiple feedback loops. So this is the second system. So that controls basically the extracellular compartment size by changing its sodium content, right? If you increase sodium, the compartment size goes up, like it follows the water retention, etc. So here the mechanisms are a little bit more controversial. There are more factors that affect the sodium intake and sodium excretion. So under normal conditions, sodium intake I don't know what you think. Sodium intake, we assume in this model that it's not regulated since it's almost always in our world, it's greater than the required amount. But of course, there is something called salt appetite as well. But in most cases, the kidneys are left with the responsibility to keep a balance between the sodium intake and excretion. So basically for sodium, it's all about controlling the output, and because the intake is almost always higher than what we need. And as I said, salt appetite is a bit less known than kind of the appetite for the body water. So kidneys, they adjust the sodium excretion. So usually the load is higher than what we need, as I said. And there are multiple factors here, many factors actually. So you can see in this causal loop diagram or causal structure, it shows major ones that we included in the model. So day-to-day variations in the amount of body sodium, they represent variations in the extracellular compartment and its size, right? And you see. So we included the filtered load, so the amount of kind of load the kidneys are dealing with per day, right? And the aldosterone hormone, and the kind of more recently, I mean, relatively more recently discovered atrial natriuretic hormone or atrial natriuretic factor. There are a few more. So this is a very tightly regulated system. And you may, I mean, I asked myself the question, so why is it that there are multiple hormones are doing the same thing pretty much? So aldosterone is keeping but salt, atrial natriuretic factor is excreting salt. But other than that, their time scales are different. So there are many factors, and that's because their time scales are different. They're operating at different time scales. So together as a whole, they lead to a very tight regulation. But as I said, compared to the first system, this one is a little bit slower. Like body water fluctuations are daily fluctuations. But for example, the half-life of aldosterone, which leads to sodium retention in the kidneys, the half-life was around 30 minutes. So if you look at the simulation outputs, the kind of the picture, you can see maybe like on a weekly basis or daily or weekly basis. So you can see the regulation of sodium is done in a kind of on a longer time horizon compared to body water, which is kind of faster. So, and then, so I built the model under 9 sectors, separated into 5 sector groups. They correspond to body water, sodium, hormonal system, the urinary sodium concentration. Endocrine sector has 3 different hormones which I introduced previously. And then we extended the model to include the treatment sector and related options, basically diuretics, aquaretics, which are basically antagonizing the effect of antidiuretic hormone, and the saline infusion or the intravenous treatment. So what happens when you combine these 2 diagrams? So there is something on the chat window. Was that for me? Maybe I missed it. Sorry about that. Can you explain what you intend by time scale, half-life? I mean both of it. Yes, both half-life and also like half-life for antidiuretic hormone, for example, is about around 6 to 8 minutes. For aldosterone, it's about 30 minutes. So when you look at the at a meaningful simulation result, for body water, you can see meaningful daily variations within few hours. But for salt, you can see meaningful variations within days. So that's what I mean by time scale. That also corresponds to the importance, right? So for example, for extracellular volume, there are some defense systems, right? But blood volume is more important. It's like your little kid that needs a bit more attention. So that has other feedback loops associated with it, or blood pressure, right? So there is a system within that system. There are multiple feedback loops at different times, operating at different time scales, and maybe additional feedback loops operating to protect a sub component under that system. But what you need to keep in mind maybe is the first system that regulates the sodium concentration is faster. The second one, that's about sodium retention, extracellular volume, is a bit slower, but, which may have consequences for treatment, but of course it depends on case by case. So I want to introduce all of these sectors. So this is an example Stockhold diagram for body water sector, and there's a representative graphical function which defines the blood volume as a function of the extracellular volume. So it's pretty much robust because, as I said, blood volume cannot fluctuate as much as the extracellular compartment itself. It has to be regulated more tightly, but since we were not so much interested in the mean arterial pressure itself, that part is a bit simplified. I mean, still relative to the other parts. So we assumed drinking and insensible loss because there's a continuous escape in the form of evaporation, right? And then there's a varying urinary loss. So these are the three sources of intake and output from the body. And then when you model the drinking behavior, of course, I realize that you have to model the continuous and discontinuous versions. So in normal life, do we drink continuously? No, right? We drink once in a while. So as you can see from the figure, I have results for both of these versions. The continuous version of the model shows a steady state behavior when all levels are initialized at equilibrium values. But in reality, just keep in mind that all these variables demonstrate a kind of a small daily variation, right? And this one, the one on the right, this continuous drinking version of the model, it demonstrates the normal daily variation in the key variables. So the main change basically can be seen in the dynamics of the urine flow. Drinking, the urine sodium concentration, since water is lost continuously, then replenished by drinking. As a result, total body water is maintained within normal limits. So there are some classical tests in the literature. So we didn't need to kind of create some situations to test the model for validation. So there were already some classical tests provided in the literature. So these are mostly from Guyton's book. It actually is an extreme condition test. So what happens to your, what happens if you drink 1 liter of water at once? So the dynamics of body fluids after water loading, you can think of it as similar to sugar loading, maybe for diabetes. So it's one of the fundamental tests to look at the interaction between body fluids and the kidney to see if the kidneys are operating the way they need to operate, right? So the urinary excretion dynamics are shown here compared with the experimental data. It increases about 11-fold within 1 hour and it ceases after 3 hours back to its normal value. But the important point here is at the same time, the sodium excretion remains relatively constant during this time. So they're not too much affected. And this is another, another schematic presentation from Guyton's book that shows the normal physiological relationships between blood sodium concentration. Here it's called extracellular osmolality, but now at this point, you know, it's pretty much the same. Antidiuretic hormone concentration, urine osmolality, urine volume, right? Urine osmolality is proportional to plasma or the blood level for antidiuretic hormone, but of course the urine volume should be inversely related to urine osmolality. So in the base run, the model simulated results for that relationship are given here. There is another comment on the chat window. Have any of you noticed that? Okay, sorry, this one is not about me, yes. So another question, what happens to your blood volume if you drink too much or too little? So we expect the blood volume not to be affected, right? So the blood volume shouldn't be affected by drinking. And here we show that it is the case. We vary the daily intake of a person from its normal value, which was about 2.2 liters, I think, in this simulation, And we use the kind of basically all the parameters come from medical literature. Blood volume stays almost constant under normal conditions. Neither the blood pressure nor the blood volume are much affected by changes in the daily intake. Maybe a more important question is what happens to your blood sodium concentration if you ingest too little or too much salt, right? If you vary your salt intake around 25-fold, like 5 times less than normal, 5 times more than normal, what happens? So in a normal person, it is seen that blood sodium concentration, if you look at the scale, it's actually it's a very narrow scale. So basically the blood sodium concentration is kept within 140 and 145 milliequivalents per liter. So it's a reasonable, it's controlled within a reasonable effectiveness, even with large changes in sodium intake, as long as drinking is enough to balance for the losses. So then I conducted some kind of knockout experiments, like the first one here. What happens if to your blood concentration if you knock out the first system as a whole, right? In this experiment, the effect of antidiuretic hormone thirst feedback system was investigated, and the effect of it on blood sodium concentration. So as you can see, under normal conditions versus after the antidiuretic hormone and thirst feedback has been blocked, only if you block both of them, I mean both of these factors, the first system as a whole, if you block both of these feedback loops simultaneously, then hyponatremia develops. Otherwise, hyponatremia doesn't develop. And one may also think that since aldosterone plays an important role in body water and sodium regulation, or maybe if you block the aldosterone feedback system, it may have a huge effect on blood sodium concentration. But that is not the case. Almost nothing happens if you block the aldosterone feedback system, which means this feedback system, even if they are very tightly coupled and regulated, they by itself cannot harm the blood sodium concentration regulation. So basically the ratio stays constant, but the numerator and the denominator, they cannot be controlled anymore. But the ratio, we can still regulate the ratio. So that's what it means.
Can you go back to the previous slide? I didn't make quite the switch from that one. So what's the?
Yeah, here, these two experiments are about blocking the first system, the first feedback system, and the second feedback system. What happens to your blood sodium concentration if you block antidiuretic hormone and thirst? Can you control the blood sodium concentration?
Oh.
Not really. I mean, during a wide variation of sodium intake, that's what I mean. So you vary the sodium intake kind of 25-fold, 5 times less, 5 times more, while at the same time you block the first system. What happens? Then you cannot regulate the blood sodium concentration anymore. See? So this is the red line. As you increase the salt intake, the red line, of course, it's kind of, there's a slight increase, but still it's a relatively good regulation. But if you block the whole system, you cannot regulate that ratio anymore. So that's what it shows.
So now this slide is ADH blocking, and then the next slide was.
And the next slide is what happens if you block the second system.
Okay.
But yeah, the second system, and mainly since aldosterone was the kind of the renin-angiotensin, aldosterone is kind of the main building block, main hormone that leads to sodium retention. What happens if you block it, right? If it doesn't work, can you still regulate your blood sodium concentration? And it seems, yes, you can. Even if you block it completely, you can still control the ratio, but not the respective numerator and denominator anymore. But aldosterone still remains as like being very important in regulating the sodium excretion by the kidneys. In this case, I wasn't interested in it, but I don't think you can still regulate the extracellular volume anymore. So it's another problem. So I didn't show it, but it leads to other problems. So we understood that the first system is the key to regulate the blood sodium concentration, right? But what happens if you block only the first one, antidiuretic hormone, or only the second one, your perception for thirst? Because these are real things. Some people, they have it disabled perception for thirst, right? It doesn't work very well, but still it doesn't lead a big change in their lives because antidiuretic hormone still works. So here you can see that total body water is slightly elevated, again, slightly elevated, but still kept at a very slightly elevated level. But if you knock out both of them, both antidiuretic hormone and no perception for thirst, usually those patients who have a problem with the antidiuretic hormone, they don't present clinical symptoms unless they also have a problem with the perception of thirst, because here the blue line, you can see that it's the total body water, so you cannot control it anymore, it keeps increasing. So that one is the development of hyponatremia. So basically it shows the appearance of hyponatremia is only possible when both of these feedback loops in the first system are dysregulated. And the end point of the simulation is actually the starting point of our game, right? Because here we have a patient who have an excess 5 liters of body water and kind of lost some sodium, and we need to replenish it. This one was interesting. I kept it just for fun. I don't know if you find it fun, but at that point, since I was so much into the topic, I found it fun. So these are patients who cannot produce antidiuretic hormone, but they don't have a problem with their perception of thirst. And it's called, the condition is called diabetes insipidus. And it's a condition, it's a problem, but their blood sodium concentration is kept at a slightly elevated level. So you can see it here, the pink line, it's slightly elevated. So it doesn't impose a big problem. But the problem is they have to live a life which is not compatible with daily life, because the water turnover is increased from 2 to 3 liters per day up to 10 to 20 liters per day. Like there are some cases in which people, like some patients, have to drink 15 to 20 liters per day. So it's a huge amount to deal with. So it's not compatible with social life, but these people do exist. And it only happens when the pool capacity of the antidiuretic hormone, because there is a pool, there's a latent pool for the hormone, if you decrease it by 90% or more. So the validation of the model, I demonstrated it by behavior tests proposed in the literature, such as extreme sensitivity tests. Those were mostly indirect structure tests. I presented a selected sample here compared with real data when data are available, but of course there are other experiments which I haven't presented here. Like for example, Addison's disease, loss of aldosterone. Other experiments with changes in intake. If you don't drink water, what happens? Like after 5 days, etc. So the model passes all of these tests. The second part, now we extend the model to include the effects of potential effects of therapeutic interventions for intoxication, water intoxication. So some sectors or structures are added to the original model here for representing the treatment options. The main ones included here are diuretics, aquatics, and saline infusion sectors. And then there are other variables for game-related measurements and etc. Let me see. Yeah, diuretics, you know what diuretics are probably. Aquatics, they are basically opposing the effects of antidiuretic hormone. The difference between diuretics and aquatics are diuretics, they also cause for increase the sodium excretion, but aquatics don't have any effect on sodium excretion. So these are all potential treatment options for treatment of hyponatremia in real life settings. So finally, I developed this interactive simulation game, still while as a master student, which we call the BWaterGame. If you have a better name, if any better name comes to your mind, please let me know. So this is the main window of the user interface, but of course there are multiple different windows for user decisions, etc. Kind of historical behavior for main variables. So the player here is supposed to play the part of a physician, like a medical doctor who is trying to treat a hyponatremic patient, right? The patient who started at the end of that simulation I showed you in the previous slide. And the physician here needs to seek a delicate balance among, as we talked, weighing the risks of hyponatremia itself. So you are hyponatremic, right? You have 5 liters of excess body water, so you need to get rid of this water. And your sodium concentration is, let me see, your sodium, so these are the warning buttons. So it seems like 120. I think this one, it was a mildly hyponatremic patient. I have multiple versions, like more extreme version and mildly hyponatremic version, etc. So the challenge was to achieve those multiple goals in balance, since rapid correction of severe hyponatremia can cause brain edema, it seems. So the total duration for this game was 160 hours or 20 decision rounds. So the player can revise his decisions at each step, making use of the provided analysis tools. So decisions made by the player are, if she decides to use those, the dose of diuretics, the dose of aquaretics, isotonic saline, hypotonic saline, etc. So there are multiple options available to her. Moreover, the player can also change some of the game settings or can impose water restrictions to the patient by varying the scenario, right? And we provided a detailed description of the game in a user manual. And the players, initially I had graduate students only who play with the game. More recently, we had medical students who actually played the game and built the model as part of a course in their medical curricula, and we are trying to document the results. So these are the results of the game tests played by graduate students, engineering students. Each of the players played the game several times. They applied different strategies in their trials. These following figures, they represent the dynamics of key measures obtained from, this one is a representative player, right? So this figure displays dynamics of the player's infusion decisions, for example, the sodium concentration. So you can see that, so 120, right? It's kind of below normal already. So it's a worse before better behavior in this, for this representative player. Blood pressure is slightly high because of the excess body water, but not at the lethal level, and total excess water is, again, it kind of shows the same behavior, first before better.
Just a quick question. Were they prepped in a similar fashion to what you prepped us with, or did they receive more or less before they began the game?
Say it again. So they are given a mildly hyponatremic patient with some excess body water and
no. I mean, how much information, how much physiology information were they prepped with, similar to what you've been telling us, or more or less? How much were they taught about physics? I mean, were they learning about the system and then play the game, or did they play the game just to see how they would do without that information?
Very good question, and please keep that in mind, because this is important, because for the extension of this work, we are trying to use this game. I mean, we are trying to see if we can use it as a tool for medical education, right? So, and in order to prove that you can use it in a meaningful way for medical education, so you have to pay attention to those things that you asked. I think in the initial version, I don't remember the detail, it's been a long time, but I think the user manual wasn't more than 3 pages, 2.5 pages, some background, but then they could also play the game multiple times until they kind of get familiar with the instructions and everything. I think they pretty much understood what was going on, but not everything, of course. But with doctors, that's a different story. They already know about it to some extent. So I think that is important, and that is about I think I have some questions for you when I come to that point. So, so let's focus on a comparative evaluation of some key performance measures. Here I have 5 players. So this one shows our key variable blood sodium concentration, and the second one is total body water. So you can see how different players' results, simulation results look like. Player 4 did not change the blood sodium concentration noticeably. Player 3 decreased it. Trials of players 2 and 5 seem to be the most successful ones, right? But then player 5 continues to increase the blood sodium concentration, which seemed to be a good thing. However, player 2 couldn't sustain the elevated level towards the end of the game. So, I mean, it's a dynamic situation, of course, so they can be analyzed separately. But here, you see something else. So dynamics of mean arterial pressure and the hourly correction rate. So player 3 administered a high amount of isotonic saline, I think, not even a high amount, but the isotonic saline. And then both the blood sodium concentration and the body water, they increased abruptly, and they exceeded the limits which was allowed by the simulation, which was consistent with what happens in real life. So simulation stopped due to coma resulting from exceeding of the hourly correction limits. But of course, during the game, before that happens, they received multiple messages, not just the warning, not just the change of colors of the buttons and stuff, but they also received messages about whether or not they're doing well or not. But as I said, this was the initial version of the game. This one displays the sodium intake decisions. So this is the user decisions. Among these 2 successful players, player 2, so they have had different strategies, right? Player 2 used a constant high amount of hypertonic saline. Player 5 used graded amounts of saline. So the amount of sodium lost was consistently high for the second player, because at the same time, the total body water was high. So sodium lost, so he couldn't play with that one, of course. Sodium lost was also consistently high, which basically is opposing what he is trying to achieve at the same time. So I can talk more about these, but we can come back and talk about them if you are interested. So now comes the time. So this is the after the thesis part, where my PhD student is taking over, sort of, but I'm still on top of it. So our motivation was, how can we use this model and this game for medical education? Actually, there's a group in Izmir School of Medicine. They played with this game, but they just didn't only play with the game. The model itself was included as part of their medical curriculum, or at least for that particular course. They built the model step by step, I think in 4 lectures, and after that they played with the game. So it's a different setting. And I had a meeting with them, virtual meeting with them. So they were expecting me to be older, first of all. I don't know why that was the case. So they were surprised that I happened to be younger than they were expecting. And the second thing is, they said that the model was useful, very helpful. It helped me understand the system first faster compared to traditional education. It helped me in some way. They couldn't explain it. So I think I need some help in trying to understand like how to extract that information from, and they became medical doctors. By the time I talked to them, they were doctors. But by the time they played with the game and they built the model, they were medical students. And they gave me very good feedback, but they couldn't explain why it helped them, for example. I mean, it varies from individual to individual, but it's how system dynamics helps people improve their decision making is something that is tricky to understand. Okay, simulation-based. Oh, Is there a question?
Yeah, well, I was going to comment. That's an interesting, I mean, important observation, or profound observation with no answers, I guess, is recognizing that something helps you learn.
Yes.
Is completely different from understanding how it helped you learn.
Oh, yes, exactly. I wanted them to document it for me, and they couldn't do it.
Yeah, I mean, so from our point of view, we would really like to know what is it we're providing people, or why even for us, why does system dynamics help us?
Yeah, we have to measure it somehow to prove it to people, right? How can we measure it? That's the question.
And knowing that it helps you is one thing.
Mm.
Understanding how and why it helps you is a completely, different level of awareness.
Yeah, I totally agree on that.
So that's all. Yeah, that's all I want to say there.
That's all?
Yeah.
Okay. So I looked into the literature for simulation-based learning. I think this one may be of interest to Bob, actually. So interestingly, simulation-based learning is comprised of mainly 4 different schools of thought, it seems. So one in management education, second in medical education, technology-enhanced simulation-based learning, and then learning theory development for simulation-based learning. And it turns out the simulation-based learning researchers in medical education and in management education, they have progressed on parallel tracks leading to, the paper says, leading to the balkanization of knowledge. So it's kind of, they're progressing independently from each other, more or less. And I am trying to combine them. So this may be something interesting to talk about. Let me see. And then if we divide them according to their types, there are core, cross-cutting, and I mean, there are three types of domains. I guess they call it domains. So the simulation-based learning was applied to 3 different types of domains: core, cross-cutting, and linking. And the linking domain was identified as systems thinking by this paper. So systems thinking was the linking domain that was kind of able to link, I mean, by definition, link these different domains. So I need to read more about it. If you know more about it, please feel free to let me know. So problem definition, model conceptualization. So here the experimental approach may be interesting. So this is about how to measure. How can we measure the impact of ST-based learning, right? So this is what we came up with initially. So it's still a work in progress. So first of all, we are kind of revising the interface, right? We can design them with medical professionals who know the needs and priorities for the target groups, etc. So this can be done, right? But eventually, after finishing the interface design, we have an interface which we are playing with, but we have to have it experimental, kind of a robust experimental approach. So this was the initial idea. The idea was to randomly assign students into, or kind of medical professionals, whoever plays with it, into 3 different groups. The first, we call it a control group. They learn via their traditional method, like whichever way they learn about medicine. The second control group is a classic ST-based approach, kind of as the lecture lesson in class. And the treatment group may be game-based methods. Let me see. I think this was the initial idea. We didn't change that idea.
I'd like to say something. I actually have to leave a couple of minutes early because I have another meeting with a graduate student.
Oh, okay, then let me finish, because that was the last slide anyways.
Oh, okay.
Yeah, so we are at this point right now. So we collected sample physiology questions from exams of previous years to design these pre-test and post-test. So, I mean, this is all about finding some measures to demonstrate like how we can improve or even change the understanding of medical students, and how we can contribute to medical education with system dynamics, both with the model itself or the game, right? So we created that survey template also to collect demographic data, educational preferences, etc. The model initially was built by an old version of Stella. Now we have it in Stella Architect. But then, of course, the next steps include these performance evaluation methods, right? Course contents, etc. So here, as I said, I can use your feedback here, but let me maybe formally finish the presentation, then we can open it for discussion, some main references. And this was the professor, doctor from Ege University School of Medicine, and also the director of Systems Thinking Association in Turkey here. I think Diana Fisher, you know about these people, right? You are working with them. Emre Göktepe, yes. Yes, these are people I work with. So this is a nostalgic picture from Yaman's lab, the Sestin lab in Istanbul, when I was master's student working on this model. This work was presented at multiple different conferences, etc. So I would like to thank all of these participants who contributed and acknowledge them. And thank you very much for listening.
I would just like, my main suggestion before I have to jet is consider doing some qualitative research on top of the quantitative. If we really don't understand how this works, you need to interview people, not just try to survey them with questions in a form. So we often over rely on quantitative surveys that don't end up, they tell us lots of stuff, but they don't get at that how and why. So just a suggestion that you consider more of a mixed methods design. It's a great design, I love it, but I would just include more qualitative data collection if possible.
No, I think that's a good point. Yes, that's something I did for the PhD work, and it was quite insightful. I think maybe we should at least present it as part of this experimental design. I totally agree. I think Bob gave it. It's a similar comment. Thank you.
I was going to make a comment somewhat not opposed to Wayne, different from Wayne's, but I agree with what he's saying there. But rather than ask, we still get back to the problem of asking people why, how this helped, and they can't, really describe it either. Maybe maybe this design here, maybe the only way to get that information is to try different designs and extract out from the designs which are more effective, so that they may not be able to tell us why it's working, but by giving them different ways of approaching it, we end up with some information about what worked and what didn't work. Whether or not they can tell us, we get the information
of course,
out of the data. So
Warren, sorry, were you going to say something? Look like you're about to say something. Okay.
I have two comments. One of when I was taking decades ago my physiology and biophysics, renal physiology was the most complicated part.
I know.
I mean, water balance and these various hormones and control of pH. I mean, it was just amazing.
I got an A from that course.
How difficult it was. And then the other is like, I have no idea where I heard this, and it was also years ago, but it was more anecdotal information about miners working in coal mines that would be in a hot environment all day, day long, and sweating, losing a lot of water and salt.
Other electrolytes as well, right? Yes.
Yeah.
Here, potassium, for example, was taken as a constant, but it's also another interacting building block there.
Like a couple of observations were, one was that they would eat food that was so salty that nobody else, the rest of their family couldn't even, swallow it. It was so salty. And to them, and they didn't know it. To them, it didn't seem salty. It was just.
I see. So they don't have the luxury to lose any water. So they're minimizing.
But the other related, and I have no idea, how these would interact with each other or with, your model. But the other observation was
being a little bit slightly hypernatremic, it's no problem. Yes. It's basically they're gaining the advantage is higher than what they lose, which is being slightly hypernatremic. But yes, that's a good idea. But they were not even aware of it. So that's interesting.
They would drink, they would come out of, the mine, have access to food and water, whatever, and they would drink a huge amount of water.
Yeah.
But they would stop drinking. They would drink an amount that was appropriate to their physiology. But they would stop drinking before the physiological signs
yes
balanced out, so that somehow cognitively,
there are additional feedback.
They have a thirst drive, but cognitively, the amount of water that they take in actually, from a cognitive point of view, tells them when to stop drinking before the other physiological factors.
The blood sodium concentration is not there yet, but I think that happens to some extent, to a much less extent in our lives as well. I think it's another feedback. It's kind of a shortcut feedback that comes from your gastrointestinal tract, something like that. Yeah. It's kind of the perception of, okay, it's coming, coming. So take it easy and don't delay too much, etc. Type of feedback. Yes, I think it's called sympathetic, or it's some sort of nervous system feedback. Yes, something like that. Yes. So these feedbacks are operating really at many different levels. It's like and the more important, whatever thing that needs to be preserved, the more feedback systems that are in place with a variety of different time scales. Blood pressure, for example.
So Ozge, I was struck by that comment that you made, that there were multiple hormones regulating in a similar way the same system, but operating at different timescales. As I think about sort of creating a generic system dynamics model to test, would that system be tightly controlled? My intuition is that the shorter time scale would do most of the controlling, and I'm wondering what the longer time scale hormone contributes. Do you have any insight there?
Okay, I see. So you're saying that this atrial natriuretic factor, for example, which has a shorter time scale, may be enough. It's about excretion of sodium. The other one is about retention, but longer time frame. So I could try to knock out that feedback and see what happens.
Yeah, it's curious. I was obviously trying to take it beyond water balance and just think about.
Interesting question. Yeah.
Yeah. So Khalid, who was with us a while ago, did some interesting work on in engineering around PID, proportional integrative and derivative control, which aren't different timescales. They're controlling different aspects of the gap in a balancing loop. So you may want to look at that. So when I look at generic systems that need to be tightly controlled, I think more about the PID formulation than I do about creating similar feedback mechanisms with different length delay sort of thing. But it's very curious. I really appreciate you sharing that. I need to do a lot more thinking about it. Thanks.
Yeah.
Me too. That was actually one aspect that was always interesting to me, but I didn't go anywhere with that information. Like, why is it, or how?
Yeah. Why would the body do that? That's a super interesting question. Yeah.
I have a partial answer, or not an answer for that, but an approach to that, I guess. It seems like in many cases, the short-term adjustments, they do, as you described, the bulk of the control, but they may be much more energy costly. And so to maintain that may be a faster mechanism, but to use that mechanism over longer term can turn out to be metabolically very costly. And so what can happen is that a longer term, a mechanism with a longer time scale might be more conservative of energy.
It may, the longer time scale may also prevent some of the overshoot that a short time scale, in terms of oscillation. So that's a good thought, Ed. I like that.
So, for example, for very short term, if you're lying down as we get older, you stand up abruptly and you have a drop in body blood pressure. I mean, that's a very, and then your heart speeds up and your blood vessels contract. That's a very, short term, seconds to minutes adjustment. But over longer periods of time, you tend to increase your blood volume. I mean, there's a number of other adaptations so that, and these are relevant to drug tolerance and physical dependence, because something that adapts very quickly can reverse itself very quickly. Whereas something that takes longer to come into play is going to most likely persist longer beyond when it you need it. And so in the case of drug exposure, a drug that produces a very rapid effect may not produce tolerance and physical dependence, because as soon as the drug goes away, the body goes back to normal. Whereas if you have a long-term exposure and a long-term adaptation, and now you remove the drug, you're left with the adaptation still in place, trying to adapt, work against something that's no longer there. And in effect, that is a definition of physical dependence.
Now I remember something which is very much in line with what you just said, but that's only maybe it's relevant for that particular case. So I think the issue Warren raised is still very relevant. For the case of salt, I remember from my very older readings, I think we human beings evolved in such a way that we try to keep all of these mechanisms that help with sodium retention as much as possible. So sodium retention mechanisms, they got stronger over time because we were not ingesting sodium as much as we do in modern societies, right? Sodium was important to keep because it also relates to be able to keep a good size of extracellular volume, which relates to blood volume, which is important, right? It relates to blood pressure. So any mechanism that helps with sodium retention, it developed very well over time. Is that something in line with your comments? Addiction to sodium retention.
Yeah. Thinking about how things develop. I mean, I've been focused for so long on here's this organism and what's the time course of mechanisms in the organism, short-term, medium, long-term, and the effects of drugs and so on. And it's a completely different mindset to start thinking about this over millions of years. And so I'm working on it. But
some interesting stuff.
Intriguing.
I see we're several minutes past the top of the hour, and I'm going to
I
play my
forgot
role
to
here.
show you during the
Ozge,
presentation, but I think this book should be our Bible or something like this one.
Shall I go get
1932.
mine off my bookshelf?
yeah.
Oh, you have it?
Oh, yeah, yeah.
I have all the books this guy has written. Each and every one of them. Yeah, I think it may have some answers to some of the questions we talked about here.
Ozge, can you put that book title in the chat?
Oh, yeah, sure. Let me do that.
Because it's hard to see. I couldn't
This
see.
one.
Ah, yes,
Right,
that one.
but I couldn't see it very well on the screen.
Yeah, just
Oh, The Wisdom of the Body, and the author, Walter Cannon.
yep.
Is it something a non-medical person can read and understand?
Yeah,
I think definitely,
Yeah.
yes.
it's written, it's very
And
readable. He is
Yeah, it's very
the,
readable.
he is the person that, that coined the term homeostasis, by the way. So this was a while back, but
Does he actually talk about feedback and all that in the book?
Yes, in his own way, definitely. So let me
Okay.
show you, there was another slide which, okay, homeostasis slide. Let me show you this one. We can have this. If those of you who are interested, we can have the conversation from here. So
copyright 1932.
yeah, so this is the from a presentation I prepared for medical students here at Koç University. So, okay, the idea of homeostasis goes back to Hippocrates, who thought that disease was cured by natural powers. Milieu interior is sort of that concept, again, which led to kind of the more fine definition of homeostasis. Claude Bernard, Walter Cannon. Yes, you're right, Walter Cannon, he's the guy. And Guyton. Yeah, I think I would probably put a few more people here.
That's
Yeah.
a good list right there.
Thank Ozge. This is very helpful.
You're very welcome. I'm happy to see you all, and I don't want to take more of your time. I think it's already an hour and 10 minutes, so.
Full piece of work, very thorough. I could stand to learn a ton just by going through that. I don't know if
Yeah.
you noticed Robert Becker's comment in the chat that he said that in the
Oh, I
psychology
missed it.
SIG, there's a number of people who've looked at the pedagogical aspects of SD,
Yeah, thanks,
and
Bob.
might be worth looking into there as well.
Yeah, that relates to the kind of qualitative aspects of
This is very cool.
information collection. Yeah.
Say a pre-announcement for next month's meeting.
Mhm.
Robert Hester, who's followed up with the work of Guyton, is going to be speaking to us on HUMOD. And
On what?
the software system HUMOD, HUMMOD. A different kind of simulation than we might do, but there might be some useful ideas and things to learn there. So
Mhm.
looking forward to having him come in and speak in April. That'd be great.
Robert Hester, and I think you
Robert
said
Hester,
that
University of Minnesota.
okay, so that's the Guyton group, kind of the
Yeah.
descendants of Guyton, basically, right?
Mhm.
Bob
And,
Becker,
you know,
he knows about them, I think.
Yeah, I'll send out an announcement about a week before the meeting.
Mhm.
We'll see what he has to say. But as
Great,
far as
so-
today, thank you for putting it together. Thank you for sharing with us. And
Sure, thank you.
Sandra, let me know if you'd like to see the recording. I know you weren't able to make it for the first part of the meeting, no problem. But it was recorded. If you want to let me know, you can take a look at it.
Yeah, I would love to. Yeah, so sorry for being late.
Sure.
It sounded so interesting. Yes, please.
Yeah, and
Okay,
feel
I'll
free
let you
reach
know
out
how to get
me.
at it.
Okay, thank
Mhm.
you. So it's good.
Great.
Bye.
Okay, folks, thank
Bye.
you so much. Awesome. See you later.
Bye-bye.
Bye, Warren.
Bye.
Bye-bye. Ozge, that was beautiful. Thank you.
Thank you very much for, it helped me actually to put my mind together and maybe go back to that research because we gave a break after a long time, and this presentation of the PhD student was from last year. Yeah, I need to get back to this research and speed it up. So it helped me to put my mind together. Thanks.
Yeah, good stuff. All right, we'll
Okay.
talk soon, okay? Keep in touch.
Okay.
Bye-bye.
Bye-bye.